A little too big.
Yeah, that's good. Yeah, they merged us with chemistry. The physics department always had their own graduation, but they've been messing with it the past couple of years. So it's like physics and chemistry. We're totally separate departments. It's kind of
Well,
strange.
they stick the honors with us.
Oh, okay.
After they split up, they stuck the honors, so we get the like the fine arts degrees and women's and gender studies gets added to ours as well. So I'm not really sure how they figure the division, but maybe it's the capacity of the auditorium or something.
All right. Well, how's everyone else doing? You're all done for the spring? No? Kent's not done? Is
Getting
spring?
closer.
Well, I know Clay's still going, right? Because you're
Yeah.
you're on the high school schedule.
We
I
just started finals this week.
Okay. Okay.
I
So,
handed in my grades 1 minute ago.
Yeah, I handed in my
congratulations.
grades a little while ago, and I already got a couple of emails like, questioning the grades. So I
Yep.
got
Yep.
that's
I was gonna,
exciting.
say you're not done, Brett. You're just starting. All right. So let's see. What are we doing today? Um, we're doing module 6. That's our final radio unit. As we talked about last time, in radio, you can do a variety of different things. You can do mapping, and so we did that with our mega map. You can do timing, and we did that with the pulsars. And you could do polarimetry, which we also did with the pulsars, and spectroscopy. So that's what we're going to do today. Okay. So let's see. Let's point you at a data set here. One second. I need to set this up. Um, okay. Spread you out. Chat. Yeah. Let's see. So yeah, spectroscopy. So our target will be edge-on spiral galaxies. We'll start with Andromeda because it's the closest one. It's big. It's big enough for us to resolve, even with our radio telescopes. Single dish radio telescopes, as you've learned now, they're very blurry, blur things out to about a degree. But Andromeda being so close, it's about 3 degrees across, so we can resolve it. So we're going to do kind of imaging spectroscopy. So we're going to do spectroscopy, but it's all tied to the Doppler effect. And with Andromeda, since it's close enough, we can resolve it just barely. We're going to do it in an imaging format. And then we'll look at some galaxies that are farther away that we can't resolve and they fit within our beam. And so that'd be pure spectroscopy, a slightly different type than you may have done with Opus, called on minus off divided by off or on off spectroscopy. And the things will process these data products, but then make key measurements with the goal kind of being weighing the galaxies. And so, these have all been selected to be spiral galaxies because spiral galaxies have cold hydrogen gas and hence an emission line in the radio that we can make use of for Doppler effects. And they're all edge on. So we can really pick up on that rotation. Let's see. Now, let me put up a few images before we get going. Not that one. Oh, it's gone. Let me find it again. Yeah, this will do. Okay, so as I said, first galaxy is Andromeda. Here it is in the optical. Normally you see it rotated around, but I have it kind of rotated here to be in the right ascension declination coordinate system. So it's kind of aligned with how the radio maps are going to be that we're going to make. And, big spiral galaxy, it's mostly edge on. The tip's about 70 some degrees, so not exactly edge on, but pretty close. And spiral galaxies are full of cold hydrogen gas. That's what produces the stars and the blue light and many other things that in Module 7 will focus on a wide variety of indicators of star formation. But hydrogen special, cold neutral hydrogen special, because it emits a line in the radio at 21 centimeters. So, here's your hydrogen atom. Very simple. You have a proton, you have an electron, and most emission lines that students are familiar with are due to atomic transitions. Electrons hopping from like the first excited state down to the ground, or the third to the second, releasing light. And when it makes those kinds of transitions, it releases the light in the optical or the infrared or the ultraviolet, some pretty high energy photons. Transitions between levels is a high energy process. This process in the radio is it's in the radio, so it's much lower energy, and it takes place completely in the ground state. So here you see the electron in the ground state, both before and after the transition. And the proton and the electron, they're charges and they're spinning. So spinning charges act like little magnets, little bar magnets. And maybe you bring magnets into class with you. Yeah, but students probably have some familiarity here. If you hold the two magnets in the aligned configuration, they don't want to be together, they push apart. And so it takes energy to hold them there. But if you have them in the anti-aligned configuration, they want to stick together. So it takes less energy to hold them there. And so you have these two possible configurations, and there's a slight energy difference between them in the ground state, all completely in the ground state. And to get in the higher configuration doesn't take much because it's not a lot of extra energy. Basically, something just bumps into the hydrogen atom that can give it enough energy to make that flip into the aligned state. And then it decays with a half-life of about 11 million years. And since it's so long, you may think I'll never see any hydrogen, but there's a lot of hydrogen out there. So it compensates for the very long half-life, and it shines quite bright. In fact, I probably have another image in my slide deck here. Yeah, here it is. Here's the Milky Way in galactic coordinates in the optical. And here it is at the 21 centimeter emission line in the radio, just taking that little spectral slice. And you can see this is showing where the cold hydrogen gas is in the Milky Way. It's in the plane of our galaxy. And Opus Lab 7 deals with this, and we do a rotation curve and measure the mass of the Milky Way. Here in MWU, we're going to measure the mass of other things farther away. Tougher to do. So, slides here. Right. And so, once you set up the emission line, you remind them of the Doppler effect. I bring in a little noisemaker, a little box that you turn it on. It just emits a frequency, and I spin it. And so they can get red shifts and blue shifts. Of course, those are sound waves. You got to be very clear. The sound waves, the Doppler effect applies to any type of wave. You have a wave speed, and you have motion with respect to that wave speed, as a fraction of that wave speed. And you can get blue shifts if it's heading towards you, red shifts if it's heading away, shortening and lengthenings of the wavelength. Okay, so here's a little setup for Andromeda. This is a spectrum. It's an on-off spectrum. We'll learn how to make those in a second, but this is an on-off spectrum pointed at the middle center of Andromeda. Kind of sets up the imaging that we're going to do, or how we're going to break the imaging apart. Now, I'll explain the on-off spectra in a second for those who haven't done it before. But how to do it. But just looking at the result here, we have some emission rate here, and that's due to the Milky Way, because we have to look out of the Milky Way to see anything out in space. And the Milky Way is full of gas. We just looked at it in that other image, and that gas could be red shifted or blue shifted. But if we're looking through a single line of sight, you're usually just kind of getting, you could hit multiple arms and it can be broken apart, but usually you're just getting kind of one chunk of gas, and it all has kind of a common red shift or blue shift. And so it's a very narrow line. That's what we have here. Then way over here, we see Andromeda's 21 centimeter emission. And it is at higher frequencies, so it's blue shifted. which means Andromeda is moving towards us. And so one of the extra things that we'll be able to calculate as we're figuring out the mass of the galaxy is how fast it's moving towards us and how long until it collides approximately. So that's kind of cool. We get to do a collision timescale. And then the other thing we see is the Andromeda line's pretty broad. And it's even broader than this because the spectrum was taken just at the center of Andromeda. Because again, Andromeda is bigger than our beam. We can't get the whole thing in one single observation. So this is just the center, and you see some extent. If you do the whole thing, it's even broader. And that's due to Andromeda's rotation. It's not only moving towards us, but it's spinning on its axis. So the emission over here is the side that's spinning towards us because it's more blue shifted. This is the side that's spinning away. And on the far end of the side that's spinning away, it's almost the same frequency as the Milky Way hydrogen in our Milky Way. So it's coming towards us. Here, I'll put the picture back up. It's coming towards us with some speed. And the blue side, which happens to be this one, is coming towards us even faster, like about twice as fast. And this side over here, it's spinning away from us almost at the same speed that the galaxy is moving towards us. So they kind of cancel out. And that's why it comes all the way and touches here the Milky Way mission, which isn't very blue shifted. The intrinsic frequency for this is 1420.4. So right about where we see the line anyway. Okay. So, we do a map of Andromeda. We've learned how to do maps before, so I'm not going to go through that again. We'll go straight to a data set. But kind of the nice thing about the radio is when you're making a map and it's collecting data, it actually collects a spectrum at every point. And so you have not just a two-dimensional image, you have a data cube. Whether you want it or not, you get the spectrum. And so that's kind of great. That's one of the great things about the radio. You can get spectroscopy trivially. You get it even if you don't want it. It's coming. And in the optical, that's hard, right? If you want to do spectroscopy in the optical, you have to have an optical spectrograph and all sorts of new techniques. The radio is very easy. And so it's actually a nice way to get that into the curriculum. Often when you do spectroscopy at the undergrad level in an astronomy course, they're looking at some hydrogen lamps and looking at the Balmer sequence and doing some pretty boring measurements. But here you can actually do astronomical stuff.
Dan, what's the trade-off of radio versus visual?
So in visual, you're probing like atomic transitions. So it's different science that they're learning. And that gives you lessons about not just compositions, but particularly temperatures. So there's all sorts of great stuff in optical spectroscopy that's different from radio spectroscopy. It really is about compositions and temperatures. Here, we're not really going to get temperature information, and the only line we're going to look at is hydrogen, although there are a few other lines in the radio as well. But the trade-off is it's so much easier in the radio to get spectra. If you want to measure Hubble's law, which we'll do today, it's not even the whole point of the exercise. We just get it kind of as a matter of course. It's like, oh, Hubble's constant. We just measured it. Moving on. It's so easy to do. That's kind of the trade-off.
Could I ask quickly, why is it easy to get a spectrum in particular? My impression is the bar that's picking up the signal needs to be a quarter of the wavelength that you're
Yes.
looking for, right?
Yep.
So then why does it automatically get other wavelengths? Is it
No, that's a great question. That quarter wavelength bar will have sensitivity. I guess the way to think of it is going to be most sensitive at a quarter wavelength, but has sensitivity above and below. Now, if you go too far from a quarter wavelength, you'll lose that sensitivity. But we're not going to go too far. We don't need to go too far. So we do get a broad range.
Thank you.
Typically, this telescope does 400 to 500 megahertz. That we don't want all that. Usually we limit it to 80 to get rid of the worst frequencies with the most interference. But 80 megahertz compared to 1420. So, a good width. And here we're going to be doing high resolution spectra, which are 15 megahertz. Anyway, final bit of setup before we start doing stuff is, okay, so we took a map of Andromeda and we're going to, after the fact, break it into different bands. And let's set up kind of like we've done with our other optical units. We started out by doing just red, green, blue in module 2, but by module 3, et cetera, we're doing LRGB plus narrowband. And so the luminance layer, we're going to define from here to here. And then we'll break it into thirds. The reddest third will be the red layer. The middle third will be the green layer. The bluest third will be the blue layer. And we'll also grab a very narrow band right here around the Milky Way hydrogen. So it's kind of a nice analog of what they've done in the optical, LRGB plus narrowband. Okay, that's enough setup. So I'll give you a link. This is a map. Let me go to radio. Andromeda. I'll just search my observations. You can see I've done a lot of these maps over time. I've learned that this one, it's best to do at night. If you do it during the day, the sun can bounce off the struts that hold up the receiver and mess up your image. And Andromeda's, it can mess up any image at a faint level. And Andromeda, particularly if we break it down spectrally like this, it's pretty faint. And so you can get some pretty nasty interference from the sun. So it's best to do it at night. So I'll just go to this first one here. I tested it right before the meeting. And I'll put this in the chat. Now, you all can make your own images, but probably in the interest of speed, let me make a set of images first, and then you can come back and make your own later. I'll just show you how to make those 5 layers. And so I'm going to create a new job. Okay. And I wish I could reset it to the defaults it normally comes up at, but I guess I'll just go through and explain why the settings are what they are. We're going to do the luminance layer first. And you can give it a name. So if you want to keep track, if other students are processing as well, you can name it so you can keep track of what's yours and what's not. Oh, first, let's just look at the data. These are the preliminary data products from Green Bank. The zigzag is just the mapping. Here you can see the mapping pattern. And when this data is acquired, it's acquired not in the usual low frequency mode, but a high frequency mode where it does 2 spectra over just 15, sorry, it's 15.625 megahertz, 15.625 megahertz, 2 of them back to back. So here's the higher frequency spectrum, here's the lower frequency spectrum. We don't need the lower frequency one, we just get it automatically. And in here you can see the emission line. And this is actually the emission line of Milky Way hydrogen. The Andromeda stuff, it's kind of washed out because in this whole map, the hydrogen from the Milky Way is only coming here from the center. This spectrum's averaged over the map, so you don't actually see the Andromeda hydrogen here, but you will soon enough. That's Milky Way hydrogen. And there's usually no RFI in these these narrower frequency bands, 15.625 megahertz, so you normally don't have to worry about that. And so here are the 2 maps from the high frequency spectrum. And there's Andromeda, and there it is as well. Kind of faint, but you'll be amazed at how well we can pull it out. And here's the map from the other spectrum, and there's maybe a hint of something there, but not really. Okay. So it looks like a good observation. It's always good to check. So we come back here, and since both channels are good, we're going to sum them. The spectrum's in high frequency mode. Gain should normally be uninterpolated, meaning we're going to use the noise measurement that the detector takes before and after. The image will make it in equatorial, right ascension declination. It was mapped in RA-DEC, and we're going to make it in RA-DEC, though you could make it in a different coordinate system if you really wanted to. Time delay. For luminance, we set this to auto. Remember, each sweep can be shifted. There can be a delay between the flux measurement and the position measurement, so sources can get broken up, and the time delay option auto will measure that and fix the image. And we'll do that with the luminance layer since it has the most light, and then we'll fix it to that. And basically all the layers have to be the exact same size, so we'll do the time shift correction on one and then make the other layers use that same time shift correction. And I have include raw off just for speed. If you have a bunch of students doing it all at once, it goes a little faster with the raw turned off. And since, we're on the clock today, turning the raw on just basically makes an image with no corrections in case you want to see the differences. And the difference is pretty extreme, but in the interest of speed, I'll just keep the raw off. Okay, the first frequency range, thanks to Reed, we conveniently coded up these ranges for Andromeda because it's really the only target you're going to do this with because we can't resolve anything else. You just take a spectrum. So these are hard coded in, makes it really nice and easy. You don't have to type the ranges that were in this table here. These ranges, you don't have to type them. Just pick luminosity and it puts in the full range there. Again, there's usually no RFI, so no skip frequencies. Background subtraction, default for a point source is 6 beams. But Andromeda is a little extended, so we're going to go a little bit higher, 8 beams. It doesn't really matter that much. And the default setting is bright target with airy rings, but this is a faint target, so we switch to faint target. And we're not going to measure fluxes or anything. We're going to make a pretty picture, so we'll do a display quality image. Not that it matters that much. But that's how you set the settings.
Hey Dan, can I ask a question?
Please.
Yeah, I was watching your video on this actually just the other day, and I noticed when you switch to the 2/3 display quality image, one of the things you just changed went away. Yeah, does that?
Yeah, the way Reed coded this is faint target corresponds to these 3 particular settings. He probably didn't need to include this one. But when you changed it, then by his coding, it's no longer faint target. So he set it to NA, but really that should still say faint target. It's just it shouldn't include this one. But I didn't explain that very well. Faint target just means it's a collection of presets. A certain RFI subtraction scale, a certain surface model for filling in the gaps.
Okay. I don't need to worry about it.
Yeah. It just, I would still call that faint target just with different display quality, but he coded it to, this box corresponds to all 3 of these instead of just 2.
Okay, thank you.
Okay, so I'll hit the let's go button. It's a Reedism. When he's excited, he says, let's go. And normally these take about 10 seconds. This map that we make, instead of being 6 beams by 6 beams, this one's a little bit bigger, 10 beams by 10 beams. So it should take about 30 seconds if I did my math right. So I just keep refreshing the page. Oh, mine's completed. Is that right? Yeah. And some of you are doing it as well, and you can. That's fine. And so I'm going to go back to my last one. And you may want, if you're doing this yourself, be sure that you go to your last one, not someone else's, because it will copy over their name. I learned that because a lot of students were using my data, because we collected the data during the day, and everyone's data was crap. And so we tried to collect some more data at night. Not everyone got it. So a lot of students were using my data. And so in real time, this became a mess because everyone's stuff were piling in there. So to make the other ones, go back to yours just by clicking on it. And then you're going to create a new job. And these can be run at the same time. So the only differences are we turn off time delay and turn on custom. That's going to force it to use the same time delay correction value as in the luminance layer, so they'll all be exactly the same size. And you need that for the combination in Afterglow. They have to be the same size. And then we'll switch to the red layer. And that changed one of the frequencies here. Everything else stays the same, so let's go. While it's running, I can create a new job and still stay on custom. I'm going to do the green layer. Let's go. Create a new job. Blue layer. Let's go. Create a new job. And then finally the Milky Way H1. That's our narrowband. It's like using H alpha in the optical, but it's H1, Milky Way H1 here in the radio. Let's go. Okay, and so they're cranking through. Now, right now, this is set up that it processes the data sequentially. I should say this whole interface is a total hack. It was never in Skynet 1. It's going to be beautifully integrated into Skynet 2. We never intended to put it in Skynet 1, but since Skynet 2 has taken a while, Reed just hacked it in here. It's not the prettiest thing. And on the back end, it's not multi-threaded. So it's actually processing ours one at a time. But all mine are done now. So I'm going to go back 1, 2, 3, 4, 5. Find my first one. And you all should download now. So everyone, actually, to make it simple for you, you can just download the 5 so you don't have to hunt and peck around for them. You can do the 5 at the bottom. Start with the one at the very bottom. These are identical to the 5 I just processed. I just did it before the meeting. You click on it, you check, yep, that's the luminosity layer. I'm going to download it. So everyone should do this now. So there's the red, download it. That's the green, download it. Here's the blue, download it. And here is the narrowband, download it. Okay. So now everyone has their own 5 maps taken in these different frequency ranges. So go to Afterglow and upload them to your workspace. So I'm in my workspace, I'm going to upload, and these are fairly small. I'll upload just so you can see how fast they go, but you all should upload your own. And once you upload them, you find them, you're going to search on Andromeda, and going to open the 5 of them. They'll open real quick.
And did we find those in group observations or collaboration?
In your workspace, because you just grabbed them from this page here. So you download those 4 or 5 and then upload them.
Okay.
Yep. Now there is a sample somewhere. If you go into the Afterglow sample workshop Andromeda, there's a set that you can use as well. But I'm walking you through closer to what you'd be doing with your students, where that each process their 5 layers, download them, and upload them. Okay, so let's take a look. Now remember in the radio, you get many layers, and kind of the clicking on the group layer, it's just nonsensical. It's that first layer in the group that matters. So there's the luminosity layer. There's Andromeda resolved. And see how great the background subtraction is and the RFI removal? Remember how messy it was in the Green Bank page? And this is what you're left with, very clean. If I go to the next one, the layer is called main. If you can't see it, you put your cursor there, you can drag this over. You can see it's called main. But you gotta be right on that spot right there. Here's the red layer. So it's on one side. Here's the green layer in the middle. Here's the blue. And this last one here is the Milky Way narrowband. I'll zoom to fit. And it's all over the place because that's in our galaxy. We're looking through this mess to see Andromeda. It's just cool, by picking the right frequencies, all that disappears and we can see the rest of it. I'll pause here. Everyone who's doing it, do you have your images in Afterglow now? Okay, great. Anyone need another moment? Okay. So now what you do is you got to split out those mains. So for each main, you right click, remove layer from file. It becomes its own separate layer, which we'll then group in a second. Here's a main. remove from file. Here's a main, remove layer from file. Remove from file, and then the last one. And once you remove them all, click on them. Just the single layers, not the rest that was left behind. Click. And this one. And then group them. So we pull the main out of each one of these and put them into a single LRGB plus narrowband group. It's usually at the top here. Yeah. Luminance, red, green, blue, and then the narrowband. And I'll pause here till everyone has their own group going.
I have it, but it looks really weird. Maybe,
Oh yeah, the if you click on the full group, it will look weird.
yeah, that's
Yeah.
what I got.
Yeah, we still have to color these and set the
Got
blending modes and do all the stuff we do with optical images. But you
Right.
can just check LRGB narrowband.
Is there a way by looking at the header or something that I can tell which one's which if I forget? I mean,
The
I can see today the
Yeah,
same numbers as you, etc. But
normally what I do with my students is when they split them out, they rename them.
mhm.
Though one person was clever and they actually put that in the name. One Kent was thinking ahead, so he actually stuck it in the name when the file was made.
Yeah.
Yep, that's good. Fortunately, there aren't too many, and it will maintain the order that we downloaded them. So LRGB narrowband. Now, okay, let's keep going. Just as we did with our optical images, we're going to take that narrowband layer, move it to the top, and turn it off. We'll start by making the LRGB combination, then we'll blend in the narrowband on top of it. So move it to the top and turn it off. Then for the rest, for the luminance layer, we color it gray. And we take its blend mode and turn that to luminosity. That's what makes it a luminance layer. All the signal to noise will come from this layer, and the color will come from whatever's beneath it. For the other ones, here's our red. We just color it red, and it can keep its default blend mode. The next one we color green. And the next one we color blue.
Is there a way to tell from the numbers which is red, green, and blue? I'm sort of trying to
Yeah,
match.
yeah, same question Seth asked.
Sorry.
They're in the order that we processed them. So it'll be, well, here's our narrowband, but we move that to the top. But L, R will be the upper left, G is the middle, and B is the lower right. That's the order we processed them, LRGB, so that's the order the numbers are as well. But if you want, you can rename. Like here, I can rename this layer L.
No, don't rename it. Because I'm matching up the number. I'm matching it up by numbers.
Oh, okay. Let's see.
That's okay. I'll just say the one that's not there is L.
Well, I just renamed it in my interface, not yours.
No, I know, but I'm
68.
watching your screen.
Okay,
And
let's
I'm
see.
coloring mine according to the numbers on your screen because I don't remember which was first.
Okay.
Yeah, L was 68.
Okay.
There, stuck it back for you. Okay, now if you come to the total combination, it's gonna look, we're getting closer. Okay, we can see it rotating, but let's process it just like we'd process an optical image. Everyone ready for this? Okay. So we go up to display and we select the luminance layer right here, the gray one. Going to link all layers to it percentile. We can't do it pixel value because we can't calibrate this. We don't have any background stars to calibrate. So we'll regress and go to our percentile combination. Now everything's tied to the luminance layer. I'm going to stick it in midtone and hit default. Looks pretty good. Remember, if you want to make it fainter, you up the midtone level. If you want to make it brighter, you lower the midtone level. But actually the default's pretty good. Okay. You could also play with the background level if you want, but in the interest of time, we'll just go with that. And once you have that, this is just for fun now. Let's put in our narrowband, which is the Milky Way hydrogen. So for that, we turn that layer back on. It looks like garbage initially. So you select it over here. And let's give it a color instead of the rainbow map. I like to color it Bomber because that's what we, for in optical images, H alpha, we color that the Bomber color. This is not H alpha, it's H1, but it's, by analogy. I'm going to unlink it from the luminance layer and maybe hit the default preset there. And yeah, so we're looking, again, you can fiddle with it. If you want to dim it down, you can reduce it. You can up the background level to darken it a little bit. There are things that you can play with on the aesthetics front. Anyway, so what we're looking at here is we're looking through the Bomber colored gas in our galaxy, and then we see this other galaxy off in the distance, and you can tell that it's spinning just from the color. This is a Doppler image instead of, it's a different type of imaging technique. And Rachel was in my class when we did this like a week or two ago, and we had I heard five, get my thumb in the camera, five people say, "Oh, this is so cool." So they were really tickled by it. They really liked it. They really got that this, they're seeing physical motion here. Now, and of course you can spit it out as a JPEG and print it out and put it on your fridge or something. Okay. And we actually made like buttons and stickers and handed them out to the students. They had Andromeda pins and whatnot during the final exam period. Let's do some calculations. That was the fun part. Now we'll do some calculations. And if we don't get to all the spectroscopy stuff, we'll tackle that next week as we move in, before we go into module 7. So calculations. Here's a spreadsheet. It's a copy of the one my students used. I'll put it in the chat. Okay, and it has tabs for all the different spiral galaxies that they'll be choosing from. But the first tab is Andromeda. Slightly different calculations here, but
Getting an access error.
oh, yeah, I made this copy, so I probably have to set the. Okay, you all have access now. And so feel free to do the calculations along with me. Our teams you can use your name instead of a team name, or you can make a team name just for yourself, whatever you want. Okay, this one's kind of straightforward because the frequencies are set by the bands. When we do the spectroscopy, they'll measure the frequencies, but here it's set by the bands. The center frequency is going to be the center of that green band. So here's the green band going from 1421.3 to 1422.1. So the center is 1421.7. Okay. And the other one we'll need is one of the edge frequencies. We'll come back for that in a moment. So we can now calculate the line of sight velocity using the Doppler equation here. I spent some time with the students going over it, but it's basically the emitted frequency, which is right here, 1420.4, 1420.4 minus the observed frequency divided by, it's actually observed frequency. With frequent, we learned it's like with wavelength, it's change in wavelength divided by emitted wavelength. But in frequency space, it's change in frequency divided by observed frequency, the way the math works out. And then you multiply by the speed of light, the wave speed, 3e to the 5, that's listed here as well. So you can code up your own, or you can just drag down. Seth, you probably need the speed of light in there. There you go. Okay, so it's coming towards us about 300 kilometers per second. So we can calculate a collision timescale if we know the distance. And there are other ways to get the distance. Standard candles in Andromeda, like Cepheids. So, and that's part of the Opus curriculum. I just have the students Google it. Distance to Andromeda in kilometers. 2.4 e to the 19. And then collision timescale is, and it's over here, distance divided by the absolute value of the speed, the distance divided by the absolute value of the speed. And that will be in seconds. So you want to divide by number of seconds in a year as well. 3.15 e to the 7. So you get about 3 billion years. And that's probably what you've heard. And in fact, I'm not going to try the spiral galaxies today. We're just going to kind of go slow and enjoy the rest of the calculation and throw in a few extras. I got a nice figure here. Here. You've probably seen this before. Kind of a, as it says, illustrated sequence of the collision. There's very little lateral motion. I think there is some, but we're just going to assume there's not any, and assume it's all radial. So here's Andromeda now in 1 billion years, 2 billion years, and 3 billion years. And we collide. When the galaxies collide, the stars won't hit each other. The space between them is so big, they'll just pass right through, but the clouds of gas hit each other. And that causes them to collapse and form all the remaining stars they would have ever formed slowly, all at once. So all the gas collapses and you have a starburst scenario. This kind of leads into stuff in the final module. And not too long after that, the massive stars, like 1 million years after that, we talked about 3 billion, just like 1 million after that, the massive stars will supernova. And so the sky will just be like a fireworks display with supernova going off, I don't know, like every day, every week, something like that. And then they die out and you have no more new stars because there's no more gas. And it will, here you see the two galaxies kind of swirling and mixing, losing their ordered motion. And here we are a little bit later when even more of the bluer stars have died. So now we just have kind of whitish stars and eventually just be red. This is kind of like a globular cluster. They don't form new stars, so they've gotten quite red with time. And the motion is usually disordered. Normally when two spirals collide, you get disordered motion, which makes you an elliptical. Sometimes some ordered motion remains, and then we call it a lenticular. But that's the only difference. Lenticulars in every other respect are ellipticals. They don't have any fresh gas, no fresh stars, no fresh star forming regions, etc. So we become an elliptical galaxy. So it's nice foreshadowing for stuff in the capstone unit, module 7.
Dan, what's the how long does this like collision period where you're getting all these supernovas going off last for? Have we ever seen that happening somewhere?
Yeah, a good example. This is not a collision, but it's a close encounter between the Cigar Galaxy and Bode's Galaxy, two favorite astrophotography targets. And often these are ones that are targeted by the students in Module 7. One group will do one team will do another. And just the close encounter caused disruption of enough gas that it formed a lot of stars, and then those stars all supernovaed at once, blowing out these kind of H alpha, not really jets, but just lifting off. It was mostly central star formation and supernovas, blowing it out there. So it's still a spiral, but there are other cases of total starbursts. Cygnus A.
Isn't the antennae galaxy
Yep, that's a
one?
great one. I don't have that picture in my deck,
Mhm.
but yeah, that's one that two galaxies doing a dance, merging. Um, you have a number of cases like that. Cygnus A, the famous radio source, it's two spirals just slamming right into each other. It's farther out and not a great astrophotography target, but antennae is a great example. Okay. All right. So this is just a little bonus, right? We got the line of sight velocity and we calculated something from it. When we do the spiral galaxies, they're a little bit farther out. They're all moving away from us because the Hubble flows. So the little bonus that we'll calculate, given their distance, would be the Hubble's constant.
Wait,
Okay.
how'd it go? Did you stop by your English teacher?
I got her. Okay. Edge frequency. So let's do the primary calculation, which is weighing Andromeda. So the edge frequency, let's go back to that diagram here. So the far edge of the red filter, 1420.5, or the far edge of the blue filter, 1422.9. Pick one or the other, doesn't matter. We'll get the same result. Well, now I've forgotten what it was. 1420.5 or 1422.1. I'll do 1422.1. Yeah, we split it halfway. Okay. So let's calculate again the same Doppler equation. In fact, I probably can just copy, paste. The logic will copy over. I got the blue side. Clay, I think yours is wrong.
Yeah, did it ahead and to put the wrong frequency.
Oh, okay.
The right one in.
So on one side, the blue side is coming towards us even faster, and on the red side is barely coming towards us at all. I think you'll still be negative though. Something's up. Oh, you got yours backwards. The 1420.4 minus F4 is what you want. Yep, you got it. Okay. So the rotation speed is just, it's listed down here. It's the absolute value of the difference between the edge speed, say equals absolute value, edge speed minus line of sight speed. So that's the rotation speed. And Rachel can attest, this is fun. Like in my class, I have 100 students, right? And so you got 100 of these lines going on all at once. So it's really busy, really active. And it's really helpful doing it this way in a spreadsheet that's, up on the screen. Because if people make calculational errors, get things wrong, they see it immediately and they can fix it. So it's a really nice thing. Like here's my students' Andromeda. And these are just, popping in real time. I go over each calculation, they do it. Oops, didn't want to close it. Okay. Anyway, back to ours. Okay. I did something wrong here. What did we do wrong?
Wait, what's the
We
problem?
need to subtract away the
I think our
the
edge
line of sight velocity before we. Oh,
let's see, when I copy and pasted B3, 3. Yeah, these two are totally not right. I'm just gonna type it in and see what's going on. 1420.4 minus this Divide by this times 385.
Wait, what's the problem? Is it shouldn't the rotational speed be the
It should be the same for
But-
all of us.
but
And
we are doing it as the speed of our edge minus the
minus the
same.
speed
So
of the
since we
center.
so minus the speed of so shouldn't it be speed of one edge minus the other edge?
No, minus the center, but you got the right answer. Why is our answer wrong? Let me check my students. It's got to be some total brain fart here. Oh, 1422 point. I think I got the wrong number off here. Let me see. No, I took the edge of the green filter. The edge of the blue filter is 1422.9. There we go. Okay. And so, yeah, we're getting the blue edge is about twice as fast as the center. The red edge is close to zero, but the rotation speed, we all got kind of the same value. Okay, great. Now, to calculate enclosed mass, I'll just jump ahead a little bit and then we'll come back and do this measurement. Enclosed mass, I derive it for the students. It's pretty straightforward, but the end result is enclosed mass is rotation speed squared times the radius divided by g. If you want to see the derivation, it's what is it? Rotational acceleration is v squared divided by r. You set that to gravitational acceleration, gm over r squared. So solving for m, you got v squared times r divided by g equals m. There it was real quick. There's our equation for acceleration, circular motion acceleration, gravitational acceleration, and then solving for m. So if we want to calculate enclosed mass, we need to know the rotation speed, which we have, and now we need to know the radius at which it's rotating there. So we go back to our image, and we're going to start by calculating an angular radius, and then we'll turn it into a physical radius. So go back to your image, use the measuring tool, which is this one, 4 squares down. Click near the center, click somewhere near the edge. It's not going to be super precise. That's astronomy for you. And look at the length here. Here it is in arc minutes. I got 85, but you'll get whatever. Go with your own measurement. I got 85.5. That's arc minutes. Spreadsheet wants it in degrees. Divide by 60. So I got 1.475. Clay got 1.42, and etc. Okay. Now to get physical radius, that's just the small angle equation. And it's here as well. You just take our angle in degrees, divide by 180, multiply by pi. In Excel, you got to give it parentheses there. Then you just multiply by the distance, which we already have over here. So there's the radius in kilometers. Okay. And then enclosed solar mass, we use this equation, and that will get it in kilograms. And down here, I give the mass of the sun in kilograms. So we divide by the mass of the sun, get it in solar masses. So it's equal to velocity squared, rotational velocity squared, times the physical radius, divided by g, which is 6.67 e to the negative 20. Then we divide by the number of kilograms in a solar mass, 2e to the 30. And we get about 300 billion solar masses, which is about right. The Milky Way is, I forget what our mass is, but they say it's like 200 to 400 billion stars in the Milky Way. That's probably 200 to 400 billion solar masses for the Milky Way. And here we're getting 300 billion for Andromeda. Uh, Good, makes sense. So, yeah, I was hoping to do a little more today, but it's probably better to go slow. And I think we probably have a meeting and a half of stuff to do for Module 7 anyway. So next time we'll start by doing spiral galaxies. It goes pretty quick. We don't have to make a picture because they're smaller than our beam. We'll just end up with a spectrum and we'll measure the central frequency and the edge frequency from that and do similar calculations, except instead of a collision timescale, we'll measure Hubble's constant. I can even preview a little bit here, but my students did. They all chose a different galaxy. Each individual had a galaxy of their own. And so you can see the Hubble's constants that they derived. They vary a lot galaxy to galaxy, but here's like the median from each one and then the medians of the medians. And so pretty close to 70, not bad for just a few nearby galaxies. So that's fun. But the key thing they're going to get are masses for their different galaxies. And that compares back to Andromeda. Andromeda kind of sets an expectation, and they're all going to be, hundreds of a few hundred billion. Okay. Anything else? Or any questions I should ask? It's it's one of the smaller exercises, like the pulsar exercise. You could do it in 2 classes. This one you could do in 2 classes, and good fundamental concepts like Doppler shift and spectroscopy, and it sets them up for Module 7. In Module 7, they're going to study their galaxy in all sorts of ways. Each team does a different galaxy, and they study star formation in that galaxy and black hole emission. So all the things they learned about. And the star formation, indicators of star formation. Is there gas, cold hydrogen gas? Well, we learn how to do a spectrum here. Is there other things like blue stars and dust, etc. So here this is building up the final skill, learning how to do spectroscopy and H1 detection for the caps.
And
Yes.
so what courses are you incorporating the MWU stuff into?
So I made my own course. So I have a whole course called Astrophotography of the Multi-Wavelength Universe, and this was the third time we offered it. And this time the room holds 100. It's one of these kind of advanced teaching rooms where there are like 9 monitors and students can control them, and they're on wheelie chairs and can move around. And we maxed out halfway through the registration period. I probably could have gotten like 150, maybe 200 if I had a big room. It's gotten really popular really quick. And we're going to be putting in a proposal. Rachel's helping on that to whatever's left of NSF. And we're writing it this month. And one of the things that we're going to be advocating, not all the participants have to do this. The participants will need to incorporate the stuff into some of their classes. But basically the story is for the traditional lecture plus 1 credit lab. That's what Opus was designed for. You can substitute that in. It parallels nicely the standard lecture, which is kind of walking through the cosmic distance ladder. The idea is you flip it around, that instead of lecturing and them having to memorize facts and things for exams, you use astronomy. It's unique. It doesn't necessarily, most of them aren't going to take another STEM course, or a few of them will be inspired enough to become a major, but then they kind of start over with major courses. Instead, maybe we shouldn't be lecturing at all, but we should be spending all this time teaching them what science is by doing science. And the nice thing about the MWU curriculum is it covers the full spread from solar system out to galaxies, but it's orthogonal. We don't do cosmic distance ladder stuff, except a little Hubble's constant calculation we're going to do. It's completely orthogonal to Opus, so it doesn't step on it. So kind of the thinking here is you should take a whole course and turn it into this.
But do you do it as a 100 level course? It's an
Yep.
introductory course? Yeah.
Yep. It's one, though I do require them to have taken one other astro or physics course. The second year, I didn't enforce that requirement. Didn't work out to my expectations. I had about one third of the class. This was their first science course, and it didn't work out for them. But if they take anything like physics for life scientists, we had a ton of them in there, and it worked out great the semester, I think. We still have to process the surveys, but we'll know soon. You'll be hearing from me more about the grant proposal in the weeks to come. All right,
Thank you.
we're at 4.
Hey Dan, just FYI, I didn't have enough credits to be able to do the observation.
Oh, okay, yeah. Are you in the MWU group?
Yep,
Okay, let me go there.
that was my confusion.
Just gotta find you. And let's get the right pot of money.
So many pots of money, so little time.
Give you a couple hours. If you want more, just let me know.
Okay.
Anything else?
Yeah, this
Yeah, go ahead.
MWU thing really uses up some credits.
Oh my God, it
I
does.
was surprised when I did 217 in the fall. It was like, oh,
We went kind of gangbusters and did all sorts of things this semester, and the students used almost 3 hours each. Last year was 2 hours each. This year it was 3 hours each. I thought we did less, but we actually did more, I guess. So, yeah.
Dan, can I ask you a sort of off-topic question?
Yes.
Um, I was talking with Brad Barlow when I was at UNC, and he sort of put me on the idea of using Skynet and Afterglow for doing some like outreach stuff. And so I've been talking with like a Boys and Girls Club type group here, and was gonna like do some activities with them over the summer. So I guess I wanted to just like ask what is sort of like the best way to set something like that up. The things I'm concerned about is like they've got a set of laptops, like they have like 10 laptops, and what I would probably want to do is create like 10 accounts that are like, Boys and Girls Club 1 or something like that that they could like log into. I don't know. Have you done stuff like this before?
Yeah, yeah, that's
Uh,
easy. I just create a group as if it were a class,
okay.
and let's see, creating generic accounts. Each one needs its own email address to
Okay.
be its own account. Uh,
Okay.
Normally, we create accounts for actual people, and so they have their own email. So you'll need to set up like 10 generic
Yeah. I
email
mean, I was
accounts.
just thinking, I just think that in the long run, what would probably be simpler would be, if I went back to this group time and again, for them to just have like 10 accounts rather than like as like the students rotate through having to like create new ones each time. But maybe that's incorrect. Maybe it would be easier to
It's up to you. I
okay.
mean, if you want the students to have their own accounts, just send me their emails and we can set it up. And
Okay.
at the end, you can always like take away their credits and save them for next time or leave them with some credits. But
Okay.
we can set up a new group each summer. It doesn't have to be in the same group. And
No, that's awesome. Okay. The other question I had, so how does one like purchase this semester I went and did everything through Cengage, but
yeah,
how do I send you money?
yep, that's basically how it works. So and lots of people do this. You're not sending me money, but UNC. There's a little contract. It's really just an LOI, two-pager. You just tell me how much time you want. Now, if you only need like an hour or two or three, I'll just give it to you. But
Okay.
the contracts are minimum 10 hours and they last the credits. There's a line in there that after 2 years we can take the credits back, but we never do. That's just in case we ever have to shut down Skynet, it gets us out of our legal obligations.
Yeah.
Um, but it's real simple. You just tell me how many hours you want. It goes for $75 an hour, a 10-hour minimum.
Okay.
And I send it to you. You sign it. You send it back. We get our signing authority to sign it. It takes them a few weeks to do so, but I can advance you the credits while the paperwork's being processed if it's a time issue.
Okay.
Then we send it back to you with an invoice. You pay us. We give you the credits.
Okay. Cool. Okay. Well, so I should just email you with details then?
Yeah.
Okay.
So in other words, the minimum contract, 10 hours, $750.
Okay. Yeah. Okay. We can make that work. Great. This is gonna be awesome. I really appreciate it.
Sure.
And
Yes.
then the other thing, you had sent a thing out a while back about this NSF proposal, like with the spreadsheet. And
Yeah. Just
I don't know if it was
some
too
names.
late. I added my name to it last week.
Not too late at all. And
Okay.
I'll be sending lots of emails. The more people we have on that, the stronger it looks.
Yeah.
I'm really kind of worried.
Yeah, of course.
Yeah, I'm not sure. Like I heard that this 37 directorates are being reduced to 8.
Yeah.
And so that means programs are going to disappear. I'm just hoping that there's a program to receive it and that they don't just throw it in the trash saying, well, the program's gone after I submit.
Yeah. I was pretty disheartened to hear about FET lost like a big grant the other day. So I don't know. I think this like happen a lot of physics education stuff is, like everything else, sort of on the chopping block.
Yep. Yeah. Yeah. I think education's probably going to get the biggest, can be shafted the biggest. So yeah, we'll see. Yeah, I was going to put in for 2 million. Now I'm going to try to keep it to 1 million, try to keep it a little bit smaller, safer, not do as much, but and it has to be like the best, right? And assuming they don't shut down the IU's program, it's going to have to be the top proposal
Right.
for it to be funded, I think, because they're not going to be able to give out too many.
Yeah. Yeah, no doubt.
Yep.
All right.
Anyway, we'll see.
Yeah. Well, thanks a lot. I will see you next week.
Okay. See y'all.
Bye.
Hey, Dan, real quick.
Yeah.
What was the map? What was the map depth? Is that still 0.3 degrees?
Yes. So you're putting in the Andromeda map?
Yep. 10
And
by 10, 10 by 10 degrees, 1/5 beam width.
yep. And I'm trying to remember map depth. That's
Fluid speed.
slew speed. Yeah. 0.3. Yep. For the slew speed.
Okay. 30
Yeah.
minutes, 33
Yeah,
seconds.
and click the button to observe it at night. You'll get a better image by far. It's on the first page, under the 10 and 20 for the elevation angle and the sun avoidance angle and the elevation angle are 10 and 20. There's a box under there saying only observe if the sun is down.
Only observe if sun's under the horizon.
Yeah. Yep. That's what it says.
Okay.
All right. Good luck
All right,
with that.
thanks, sir.
Sure.
Yep. Oh, hey, real quick.
Yeah.
Completely separate. I mentioned something to you a while back. I'm thinking I'm moving more towards doing this podcasting thing. You mentioned summer is better for you. What kind of schedule for you?
Oh, anything. Yeah. I don't remember too much about it, but so you asked me to do a podcast with you, I presume, and I said yes.
Yeah, basically chatting about a few things.
Sure.
MWU, if you see this other, but yeah, I'm still working out details. But now we're hitting summer. I'm just sort of wanted to just
Yeah,
bring that
whenever
up
it's
on the radar
fine.
again.
You send me some dates that work for you and we'll finagle and make it work.
Okay, good. Thank you, sir.
Sure. See you later.